Okay, it's recording. That's good. So I could have started this time. Okay, so yeah. So yeah, so let's recall what we covered in the last lecture quickly, and then we will move on. So we discussed so last lecture. So we discussed Poisson summation formula. It's a great formula, as we discussed. So basically, it says that if you have a function f from real line complex numbers, which is smooth. Smooth means I think C1 is enough, at most C2, but we can assume C infinity because we only apply it to this case. And there is also rapid decay at infinity. I mean, plus minus infinity, of course. Then we have sum f of n, and in integers is equal to sum f hat of n, again, n is integer, where f hat of n, f hat of c. So I defined the Fourier transform to be integral minus infinity to infinity, right? E to the, did I use 2 pi or non-2 pi? 2 pi, the cares of normalization, 2 pi I cx dx, f of x dx. And I should not forget minus 1 here. Okay, so this was our definition. Then we applied this to the function. So applied it to the Gaussian, right? So for that, I took f of x equal to e to the power, so some normalization, minus pi a x squared, for example. For a is positive. So the Fourier transform of Gaussian is again a Gaussian, but the difference is that the parameter here is 1 over a instead of a, and there is a coefficient that appears in front of the Gaussian. These are both are important. Okay, so this is actually is in your assignment, but I didn't want you to do it. This is a standard thing in Fourier analysis, the first thing that you do. So f hat of c turned out to be equal to 1 over root a e to the minus pi over a c squared. This is the, yeah, so yeah, this is very important formula. The Fourier transform of Gaussian is again a Gaussian, but there is a normalization in front, 1 over root a, and this parameter also changed from a to minus a to 1 over a. These both are very, very important. So I applied it to this, then we got that theta of t equal to 1 over root t, theta of 1 over t. So this is this magic formula where theta of t is by definition the function sum e to the minus pi n squared t n belonging to z, right? And this is defined for t positive. This is, of course, Jacobi's theta function. In this incarnation, you can also look at it as a function in the upper half plane if you rotate, and then it becomes honest modular form or automorphic form in that case. But for us, only so yeah, you see, we have to apply this to that, and then of course the left-hand side is exactly this part, and the right-hand side comes out to be this quantity, exactly because of this formula. Almost you can see what is going on here. Yeah, just so I went a bit fast, and at the end of the lecture we were all tired, so just there was a little bit fuzzy at the end, so I just write it now so that I'm checking it now is straightforward, right? Any question about this? Okay, so what was the application of this for us? What was the importance of this formula? Hmm? Yeah, this actually gave us the functional equation. And this star gave us functional equation for zeta. Which again, I wrote it in the form z of t, or z of s, equal to z of 1 minus s, where z of s is by definition equal to pi to the power minus s over 2. What's the next factor? Gamma of s over 2. Next factor is just zeta, right? And this is called completed zeta function, right? It's completed. In fact, not only we derive this, in fact, we also derive the analytic continuation of zeta to the whole complex plane, except 1. And at 1, we know that it has a pole, and the simple pole and all that. Okay, so very good. So this is the essence of this modularity property of theta function is the essential thing. This is very, very important. And this theme really appears again and again and again in number theory. This is like beginning of Langland's program, if you want, because that's essentially a kind of automorphic form, and so you attach to it a kind of L function, and then there is also another L function that's zeta function, and we are saying these two things are the same. So yeah, this is like a beginning of a river that goes, and then other rivers contribute to that, and at the end becomes Langland's program. So you really have to pay close attention to this function and the techniques that we used here. This is very important. Anyhow, so one of the ideas, so another idea was that we introduced, although not formally, but now I want to introduce it formally, and that's the idea of Mellin transform. That's a very, very important idea. Mellin transform. So what is Mellin transform? So basically, imagine you have a function, let f say from, yeah, open interval 0 infinity to c, yeah, be such that, okay. So first of all, let me define the Mellin transform. Its Mellin transform is the function So let me write it here. I'm going to write it here. Mf of s equal to integral from 0 to infinity f of t to the power s over t dt. That's the thing. So now, for this to make sense, we have to put some conditions, some restrictions on f for integrals to converge at infinity and to converge at 0. So for the integral to converge at infinity, I just assume that f is exponential decay at infinity. So assume f of t is less than equal to c e to the minus t as t goes to infinity. I mean, certainly this is enough for some c constant, c positive. Huh? So we usually write it also in the form f of t equal to O of e to the minus t as t goes to infinity. Sometimes you write it like this also, capital O, big O. Okay, so that certainly guarantees that the integral is convergent at infinity for all s. This implies, yeah, this implies that integral at infinity is convergent at the upper limit, at least, at infinity for all s belonging to C. But this part is okay. But this integral also can have problem at 0. And we saw that in the case of gamma function, right? So, so for 0, we assume that, so second assumption, let's assume that the function near 0 is O of t to the power minus alpha. F of t is capital O of t to the power minus alpha. Alpha is positive. Alpha is positive. Okay? So what does this mean? What does this relation mean? I.e., this just means that f of t is less than equal to some constant c. Again, this constant has nothing to do with that constant, right? Times the t times 1 over t to the alpha. Yeah, as t goes to 0. So if we have this sort of condition, it implies that integral 0 to infinity is convergent at t equal to 0 for all values of s bigger than alpha. I mean, because I'm working with complex numbers, so I better write the real part of s bigger than alpha. Do you see that? So the case that we considered was the case e to the minus t, right? So let me give you an example of this that we already considered. So here was example that we already did. We just took f of t equal to e to the minus t. So what is the value of alpha in this case? Maybe I just put alpha bigger than equal to 0. So what is the value of alpha in this case? Alpha is 0. Yeah, alpha is 0. So in this case, alpha is 0. So what are we saying? We are saying that e to the minus t is less than equal to some c, right? Which is, well, 1, in fact, as t goes to 0. In fact, for all t positive, even satisfies that condition, right? So that's okay. So this is assumption 2 is okay. Assumption 1 is also okay because this is e to the minus t. So this is assumption 1, 2. So assumption 1, of course, f of t less than equal to e to the minus t. And this is assumption 1. So both assumptions are okay. And in fact, that's what we observed. And we noticed that the Mellin transform of e to the minus t, we called it gamma s, right? So gamma of s is equal to integral from 0 to infinity e to the minus t, t to the s over t dt. So gamma function, gamma is the Mellin transform of is the Mellin transform of e to the minus t. So this Mellin transform is a very interesting transform. It just takes a function which is defined here on t positive, turns it into a function on some right half plane. This is alpha, and this is here. So this is domain of Mellin transform of f. And here is domain of f. This is what Mellin transform does. Takes a function like here, and turns it into a function and the function is holomorphic, right? This function is nice holomorphic because this is holomorphic, and the rest doesn't matter. I mean, this f could be even measurable function. That's okay. That comes out holomorphic because it's just like you're summing some holomorphic functions with any kind of coefficient you want. So because, yeah, you may see Mellin transform in other courses in analysis and in geometry, number theory. So I thought I should mention this separately anyhow. Right. So any questions or comments? Yeah. You can want to transfer the heat kernel in this vector. Yes. Okay. Yes. How is the theta function? Yeah. So let me yeah, that would be a kind of example. Yeah, indeed. So let me just write it down so that there will be some discussion now. Okay. So typically the way these things appear is, I mean, in geometry, so we have a sequence of numbers like the 1 bigger than or less than equal to, right? And so this is like a spectrum of some operator. And then we attach a zeta function to this, that d of s is equal to sum 1 over lambda I to the s, right? This I from 1 to infinity. First of all, this is now an example of a series that we already studied. And that's a Dirichlet series, right? So this is an example of a Dirichlet series. Is a Dirichlet series. I mean, the zeta function is a special case, right? 1 less than 2 less than 3 And then we got zeta of S, which is 1 over n to the s, right? Just a very, very special case of this. Oh, this is the, this is the spectrum of an operator, like eigenvalues of the operator. But this operator is on an infinite dimensional space of functions, like on a Hilbert space. So it's a spectrum has, instead of like a matrix that has finite number of points in the spectrum, you have infinite points in the spectrum. Yeah.
The transformation that its eigenvalues are 1.
Yeah, the operator, you mean? Yeah. For the case of zeta function, the manifold is S1, and the operator is 1 over I ddx, or Laplacian minus d2 d2x. That works. That gives you this. Yeah, but I'm now talking very general. You don't have to know even the manifold background or geometry background of this. Just look at it as this case. Okay, then there is another quantity which is okay. I don't want to use z of t. I don't want to use so let's call theta d of t. Let's define to be equal to some exponential of minus lambda I t. So this is in geometry and physics, this is called partition function, basically. I mean, again, this is a name that doesn't matter much why it's called partition function or why is it the generalized theta function. That's okay. These two players in the game is one is this theta again, and this is zeta. And these two things are related through this Mellin transform again. So let's compute Mellin of theta d at S. So what is it? Sum, I have to put it here, right? Sum e to the minus lambda I t to the power s over t dt, right? So this is equal to sum I from 1 to infinity integral 0 to infinity e to the minus lambda I t t to the s over t dt. Now, what is this integral? What is the value of this integral? Yeah. 1 over, sorry, lambda to the ts? Yeah. Sorry. Okay, yeah, and then? Yes, minus s. Yeah, so what we did is I proved the following relation. Lambda to the power minus s is equal to 1 over gamma of s, integral from 0 to infinity, e to the minus lambda t to the s over t dt. This I proved when I was deriving functional equation for zeta. So here you just put lambda I. So you get this now is equal to lambda I to the power minus s times gamma of s. Okay. So now I can continue this. And so this is nothing but gamma of S times zeta function. Yes. Zeta d of S. Now, the question is, what is the domain of this function now? Where is the domain of this function? Well, the domain of this function, we cannot know unless I know how this guy decays near zero, or actually grows near zero. This, without that, I don't know how it behaves near zero. What is the domain? It's the question of finding value of alpha, right? And what happens in practice is that, in the cases that are relevant for me, these are in geometry. Since you ask, I'm saying this extra thing. So in geometry, where if D is a first order differential operator, then in this case, you can show that this theta D of T is asymptotic to T to the power minus dimension of the manifold times 1 plus, so C0 plus C1 T, C2, T2. Again, you don't have to know the reason for this. I'm just giving you a scenario where this theory we developed can be applied. So what does it show? Alpha is equal to dimension of the manifold, right? So the zeta function is convergent for S bigger than dimension of the manifold, by this statement that I made. Zeta d of S defined for real part of S bigger than dimension of the manifold. So in other words, you can have situations where this spectral zeta function is not necessarily defined on real part of S bigger than 1. It can be defined on real part of S bigger than some bigger number, which is dimension of the manifold. But you don't see now this, but I'm just giving you some hint. Yeah, so, but be careful, this D is first order. Laplacian is second order. In this case, because it's second order, then it becomes dimension of m over 2. You pick up factor of 1 over 2. But again, this doesn't matter. You don't have, because this is not. But this is one of the ideas that also came from analytic number theory and then was transported to geometry. Okay, very good. Now, any questions, by the way? So the thing that you have to remember is Mellin transform and the domain of the Mellin transform. That's what really matters. Of course, there are some properties of the Mellin transform. You see, for example, Fourier transform has some properties, right? Okay, Fourier transform is a linear operator, but what extra properties Fourier transform has? Yeah, it behaves well with respect to convolution, turns convolutions into products into convolutions. Mellin transform also has those sort of property, but with the right type of convolution, which is related to this multiplicative Haar measure on positive real axis. Okay, so I can explain that later for you, but let's move on to what we wanted to do next. So another topic that we started to discuss was the special values of zeta function. So, I mean, the question is, so I want to compute values of zeta of S for certain S. And this is an important task because these numbers are important. So what values of zeta functions so far you know? Be calculated so far. Hmm? 2? Did we calculate 2? No, but it's done. Yeah, we will recall it today, yes. Sorry? Negative even, exactly, which are 0. So this we already did, zeta of negative 2n, that's equal to 0 for n bigger than or equal to 1. This, you know how we proved it, by the way? Yeah, we just, we used, in fact, the fact that the completed zeta function is holomorphic everywhere except 0, 1, and gamma has poles at negative integers. It's just combination of the two. Even you didn't have to use functional equation. Just analytic continuation is enough. You see? Okay, you get it. Okay, so this we already did last lecture. So now, moving forward, what is zeta of 0? We didn't calculate this. This is one of your assignments. This is part of the assignment 3. So zeta of 0 turns out to be minus half. For this, you need functional equation, I believe. But you will do it. So this is assignment. So this is kind of a funny thing. Sometimes people write that 1 plus 1 plus 1 plus 1. Then they make these stupid videos and put it on YouTube. You get 1 million hits over a day. And you prove Riemann hypothesis, only 5 people. No, okay. Prove Riemann hypothesis, I'm sure a lot of people will watch it, but not 1 million. But you do this, then somehow you get millions of hits. I don't know what's going on. So this is equal to minus 1 half. Yeah, there's this number file video. I'm sure you have seen these things. Anyhow, so you know why this is written like that, right? Of course. Yeah, formally they just sub in the value of S equal to 0 in a formula which is illegit. You should not put that into that formula. But nevertheless. So moving forward, of course, zeta of 1 is infinite. Yeah, so this is a simple pole. Simple pole. And then there is residue. When there is a pole, there is also residue, which is 1. This we already calculated, this part. So this is assignment. So the two of them, 2 out of 3 we have already done. And what else? Okay, so then we have zeta of 2, which is 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. So this was calculated amazingly by Euler in 1737. And you know the value? 6. Yeah, famously pi squared over 6. And you know the approximate value of pi squared over 6? I picked it up from Wikipedia. So yeah, 1.644934. So 1.644934. And anybody remembers the value of zeta of 4? So zeta of 4 must be pi 4 over 90. Yeah, this is correct. Yeah. And this, okay, so I write it down. This is 1.0823. Approximately zeta of 6 must be pi to the power 6 over 720, or is it 900? I don't know. Which one is it? 720? 945, sorry. 900. Yeah, they are 945. Yeah, pi to the power 6, 945. Huh? Pi to the power 4. No. No. Pi to the power 4. Yeah. No. Yeah, the powers are increased. Yeah. And then, so we move on. Euler continued up to zeta of 16. So he showed that this is pi to the power 16 over, yeah, he calculated it. It's not pi to the 16. It's 3617 pi to the power 16 over 3256 4156 6250. This was, huh? Yeah, I will tell you. So this was calculated. This is exact, by the way. This is not approximation. This is an approximation, but this is exact. This coefficient 1 over 6, 1 over 90, 1 over 945. And this 361 divided by that. These are exact. Yeah. Okay, I'll come to that. Right. Okay. So this was done by Euler in 1737. Certainly this one, computing this, was called Basel problem. But Basel is a city in the border of Switzerland and Germany, maybe Austria also, maybe just first two, I'm not sure. Well, this is the birthplace of Bernoulli family. And actually Euler was born in Basel, I think. And Bernoulli posed the problem. He gave this problem as a challenge to mathematicians of his time. And when, so this came to be known as Basel problem. This is Basel. And so when Euler solved this, he was a celebrity already. So this one made him really famous in its own world. So, but I'm not sure whether these are in the same paper or he calculated them later on. I'm not sure he put it in the same paper, but certainly he has a book on calculus that all these things are there. Yeah. Okay. So now the question is this. First of all, where these formulas come from? So question 1, why? Question 2. What is the question 2? No, I mean, yeah, that's it. What's the next question? How to generalize this? I mean, it's reasonable to guess that, sorry, this is going to be equal to perhaps some rational function times pi to the power 2n. Maybe. What is another question? No, this is the question, what is zeta of 3? This was the question. Zeta of 3, zeta of 5. Okay. So what are these questions? So Euler went back to this question again and again in his life, and eventually he answered this question, I think within 5-10 years after the first paper. This question was answered eventually. I will write it down. I will write the answer, and then but zeta of 3, and nobody knows what it is. We don't know. If you can come up with a formula for zeta of 3 in terms of known quantities like E, pi, gamma, Euler's gamma constant, all these things, you will get a Fields medal for sure. Because this question has been open for more than 200 years now, since the time of Euler. Euler killed himself to say something reasonable about zeta of 3. He couldn't say anything about zeta of 3. Zeta of 5, zeta of 2n plus 1. The first thing that was proved about zeta of 3 was in 1979. There was a French guy, Apéry, who showed that zeta of 3 is irrational. So that was quite a big progress, considered big progress. Zeta of 3 came out to be, he proved this is irrational. I'm not sure about zeta of 5, zeta of 7, or this thing. Now we know that there are infinite number of these odd zeta values that are irrational, but we don't know which one. They can prove that. So there are a lot of mysteries about these zetas. Maybe the secret of universe is in these zeta values. Nobody knows. Yes? No, I mean, 3 is a prime number, 5. I mean, they're far more complicated, actually, because they are all odd. Yeah, so they're completely mysterious. No, we have no idea. No, no, no. Yeah, so now let's backtrack and see how Euler could compute zeta of 2. I'm going to give you Euler's argument now. Question? Well, no, not at all. It took 250 years or something to prove it's irrational. Now, proving it's transcendental is a totally different level, right? Because, yeah, proving is irrational means that it doesn't satisfy a first-order equation with integer coefficient. Proving is transcendental means that it doesn't satisfy any nth-order equation for any n with integer coefficient. So this is far more complicated. So that nobody knows. Sorry? Yeah. I'm pretty sure. Anything you can say about these things, you get the Fields medal. But that's not, anyhow. So let me now go back to the zeta of 2 calculation. And then we'll come back after the break. Okay. So I'm going to give you Euler's first argument. That's really literally his first proof, 1737. But then he noticed that this proof has weaknesses. I will mention those weaknesses. And then he improved his method to something much more superior. So I won't discuss that right now. So what is his first proof? Okay, his idea was the following. So imagine you have a polynomial like 1 plus ax plus bx squared plus cx2. So some polynomial of finite degree, for example. So imagine this polynomial has roots alpha, beta, delta, gamma, and so on, with roots alpha, beta, gamma, so on. Then you can factorize the polynomial, right, into these products of these things. Then you write the following factorization. Then 1 plus ax plus bx2 is equal to 1 minus x over alpha times 1 minus x over beta times 1 minus x over gamma, etc. Are you with me? 1 plus ax plus bx squared plus cx cubed, etc. is equal to this, etc. That's clear because both sides have roots, alpha, beta, that have same roots, and they match at value 0, because if you put 0, you get 1 here, and if you put 0, you get 1 here also. So this already was quite a deep invention of Euler. He didn't write it as x minus alpha, x minus beta, x minus gamma. He wrote it this form. And this looks a simple thing, but it was already quite crafty invention on the part of Euler, I would say, because you'll see. Okay, so this is for polynomials. But then he takes a kind of quantum leap. He says that, well, this should be true for power series also. So apply then, next, apply this idea to power series. Okay, so before going there, let me just write something because I want to conclude this. Okay, equating, I'll write it like this, equating terms on both sides. We get that, okay, the zeroth order terms, it just doesn't give me anything, 1 equal to 1. But the first order term gives me something interesting. It tells me that A is equal to what? What does it tell me if I equate first order terms? Minus 1 over alpha plus 1 over beta plus 1 over gamma, right? And then equating next term, B is equal to plus 1 over alpha beta plus 1 over alpha gamma plus 1 over beta gamma, and so on. Product 2 by 2, etc. I mean, these are now, this is completely legit. There is nothing here. These are called Viet's formulas. I mean, you have seen, because this is just for polynomials of finite degree, right? There's nothing strange about these things. Okay, so this is fine. Completely within, this is the kind of mathematics I teach to my second-year students. Mathematical methods course last year. I'm going to teach this year again. So yes, question? This is a finite degree polynomial so far. But then he says that, okay, I'm going to apply the same principle to infinite degree polynomials, which are power series. So apply this daringly to polynomials of infinite degree. So what does this mean? It means that then get same relations as star. I mean, just write infinite number of terms on the left-hand side, infinite number of products on the right-hand side. You say that they are the same, put corresponding things equal. Already you can see that there are problems here. Okay, first of all, what does this mean? Is it convergent or not? And if it is divergent, what can you say in this case? And all these things. So there are all these issues, and Euler doesn't care about any of those. He says, let's move on. Okay, so you move on, but then he's going to apply this to a particular polynomial. That's the polynomial that computes sine of x function. So in fact, sine of pi x So apply this. Sine of pi x. So first of all, what are roots of this polynomial sine of pi x? What are the roots of sine of pi x? Just integers, right? The roots are just z, set of integers. And what is the polynomial itself? Sine of pi x. Well, we know that sine of x, right? Well, Euler already knew the Taylor expansion of psi x. Maybe he was the first who calculated it. I'm not sure. Perhaps he was the first to calculate. Sine of x expansion is x minus x3 over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial, etc. So sine of pi x, obviously, is going to be equal to pi x minus pi x cubed over 3 factorial plus pi x to the power 5 over 5 factorial, so on. It just, okay, then he says that, okay, but I know the roots of sine of pi x. So he says that, so okay, then sine of pi x must be equal to first. There is a, we cannot apply it quite to sine of pi x because this has a root x equal to 0, which doesn't appear in this. So what you do, you just take sine of pi x over x. You just kill one factor, annoying factor of x. Apply, then apply to sine of pi x over x, which in fact it starts with 1. 1 minus x2 over 6 plus x5 over 5 factorial, and so on, right? Oh, yes, of course. Yeah. I did all the work here, but then I just discarded it. That's terrible. Two. Oh, yeah. Oh, yeah. Okay, so I have to write it separately. So this is going to be pi cubed, x2, pi 5, x4, and so on, right? And 1 is a pi, yes. That's correct. I should have done it by pi x, right? And then what you get? You get 1 minus pi 2, x2 over 6 plus pi 4. Then it comes even again, pi 4, x4, and so on. Okay, now, so sine of pi x over pi x is equal to what? Because we know the roots of pi x, sine of pi x over x, these are all non-zero integers, so they're going to be equal to product of all these roots. But these roots appear in positive, negative. So each factor here appears in as two terms, one with positive, one with negative. So basically, he says that, okay, then pi 1 minus x2 over n2, and from 1 to infinity. He says that. If you want, this is another Euler product formula. It's not as important as the first one, but this is also a product formula. So this is called Euler product for sine. Okay. Now, if you compare this, compare with the star, yeah. then you get that sums of 1 over n squared is equal to pi 2 over 6. It follows, right? This is there. It's like magic. Is equal to pi 2 over 6. This is the problem. Okay. So now, any questions before we move on? Would you buy this proof, by the way? What's your objection? Yeah. This product, by the way, is convergent by the principle that we discussed, because this is summable. Sum 1 over n squared is summable. So Euler already, everybody knew that this product is convergent. So there's no problem with convergence of the product on the right and convergence of the series on the left. These are for all values of x are convergent. So that's fine. So, but
if it's formal, if they're both formal series, yeah, but okay, that's going to work.
yeah, any other comment? Yeah.
Say like formula to find.
Mm-hmm. This is a Taylor expansion. So, but is the logic flawed? The logic is flawed because we still expect to some details to be given and we are not given. But can you point out something even stronger objection to the argument? Yeah, you see, we had a fact which is elementary. You can teach it to high school students. This Viet's formula that if you have a polynomial, you know the roots, you can write it in terms of products of these linear factors. You decompose it. But the thing is that statement does not hold for power series, even if the power series are convergent, simply because. So what is at the core of his argument? His argument is that I know the roots of this function, so I know that it must be of this form. But if you know the roots, you can still have some factor like this. This has the same roots as this one. And and this is missing. In fact, I don't know how much complex analysis you have seen. There is this Weierstrass theory of infinite products of holomorphic functions. And they tell you that if you know all the roots of a holomorphic function, which is entire in the complex plane, there are some factorizations like that, but you must have some exponential factors in front. Not true that because I mean, this is obvious. This has same roots as this one. So Euler was claiming, was assuming that there are no factors here. So this is the mistake in the argument. Is the flaw in the argument. But Euler was at the same time was quite right, because the value that he computed using this, he got pi 2 over 6. He calculated this. And numerically, they matched. He was very, very careful. He didn't want to say that, okay, by some formal mumble jumble, I just push around the symbols and then I get in. No. He knew what he was doing. He checked the values and 1.6 da 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 here, and 1.6 da 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 here. They match. And by the way, he calculated approximate value of this first before starting the calculation. It's proof. So he knew what he was more or less looking for, almost. So he was quite right in assuming that there is no factor here, but he didn't have a proof of that, and he even doesn't mention that. Again, he was almost always right. Almost always right. I would say always right, yeah. Yeah, so this is the thing. I want you to pay attention to this. You see, the argument is brilliant, and it can be fixed with more theory, complex function theory and all these things. If you know a little more about the growth of these functions at infinity and this sort of things, and you know that there can't be any factor here, then the argument is solid, waterproof, and perfectly fine. There's no problem with the argument. So this was a big discovery of Euler, after all, and this is a big method. And now, how did he then compute? Okay, so this is the next thing. So how he computed these ones? How did he compute zeta 4? No. Okay, so for this, we come back after a quick break. It's a good time to take a break, yeah. So let me go to pause. Okay, so it's recording again. So let's do that. So now the question is, what is that? So Euler's idea then, again, was this. So let me write it in a different form. It's the, you see, you have some symmetric functions, right? So sigma 1, for example, equal to x1 plus x2 plus x3 plus xn, sigma 2, this you have seen in field theory at least, equal to x1, x2 plus x1, x3, 2 by 2, you take 2 by 2, distinct 2 by 2, xn minus 1, xn, sigma 3, you have x1, x2, x3, etc. And finally, sigma n is product of all of them, right? x1, x2, xn. So we have n functions, they form a basis for symmetric polynomials, right? So this is a basis for symmetric polynomials, or symmetric polynomials. But there is another basis for symmetric polynomials, which is, you know what they are. These are powers, right? So P1 equal to, P1 is the same as sigma 1, but P2 is x1 squared plus x2 squared plus xn squared. P3 is x1 cubed, x2 cubed plus xn cubed, and finally Pn is equal to x1n plus x2n plus xn to the power. You have seen this in these functions if you could. And you know that P1, P2, Pn can be expressed in terms of sigma 1, sigma 2, sigma n, right? And these are called Newton identities that relate these two bases to each other. I don't want to use all of them. There is something very simple. So how can you express P2 in terms of sigma 1 and sigma 2? How can you express P2 in terms of sigma 1 and sigma 2? You can express it in terms of sigma 1 and sigma 2, right?
Where is it?
Sigma 1 squared, right? And then subtract sigma 2. What happens? x1, x2, x1, x3. But here sigma 2 is just, okay, so if I raise this to power, I'm going to get, so what should we do then? Is that equal to that? Or? 2 sigma 2? I mean, at least for 1, you have x1 plus x2 squared, you get x1 squared, x2 squared, minus 2 x1, x2, so you have to put 2 sigma 1. Okay, so this is minus 2 sigma. And there is a formula here also, which starts with sigma 1 cubed, which I won't write it. You can work it out. And here also there is again a formula, sigma 1 to the n. I don't care. You just focus on this one. So P2 is equal to that. Now, what Euler says, he extends these relations to infinite number of them, which is okay, because things are convergent. So you say that, so x1, x2, xn up to x infinity are all the roots. So this formula that we have, what does it say? For n equal to infinity to this formula. Which is equal to 1 minus pi 2 over 6 x2 plus pi 4 over 5 factorial x4, which is equal to product of 1 minus, you remember what it was? x2 over n2, right? x2 over n2 and 1 to infinity. Okay, so the first relation gave us a Basel problem, right? The first relation we applied, it gave us sigma 1, in other words, P1 equal to sigma 1 equal to sum 1 over n squared equal to pi 2 over 6. But what we are interested now is P2, which is sums of squares of these things, right? Sums of 1 over n squared, which is n4, right? But this is equal to sigma 1 squared minus 2 sigma 2, right? Now, what is sigma 1? Sigma 1 is pi 2 over 6. So this is pi 2 over 6 squared minus, what is sigma 2? Minus 2, sigma 2. What is sigma 2? But sigma 2, you can read it here. Sigma 2 is here. 1 over 5 factorial. Minus 1, pi 4. Minus 2 over 5 factorial, pi 4. So if you put everything together, you get the following. So conclude that sum 1 over n4 and from 1 to infinity is equal to, so there is this factor of pi to the power 4, first of all. But then I've got 1 over 36. Minus 2 over 5 factorial. What is 5 factorial? 5 times 4 times 3, 60, 120. 5 over 120 factorial. What is 5 over 120? So let me put it minus. What is 5 over 120? Oh, there's also 2. No, 2 over 5. Yeah, yeah. 2 over 120, yes. So 1 over 60 then, right? Hmm? So what is it? 36 times 60. And here I get 60 minus 36. 5, 4, 36, 60. What is that? Is it 24? Hmm? Okay. 24. So then this becomes 10. What is that? 6 times 4 is 24. This remains 4, I believe. Hmm? Then 4 is 9 remains 1 over 90. So this is equal to pi 4 over 90. And this was zeta of 4. It was zeta of 4. So that's exactly how Euler calculated this. So he used this formula relating product 2 by 2 of roots, 3 by 3 of roots, so on, to powers of roots. And you use this formula, the infinite product expansion. Then you go on, you compute zeta of 4. And now you can see that zeta of 6 also is related to third powers of roots. So then you go on, and then you have to write this formula, which he did. He computed zeta of 6. And then he applied this. So he went up to zeta 16. I don't know how many days he worked. It could be that he just did it in few hours because he was very good with calculations. It could be that maybe a couple of days, but he must have used a lot of papers. I remember paper was very expensive back then. But he was in Academy of Science in Russia, so I think they gave him all the papers he needed for free. Just produce papers. We give you blank papers. You just fill it in with formulas, return it back for publication. That's okay. It was in St. Petersburg Academy of Science in Russia under Catherine, I think, Catherine the Great. Well, there was a job there. Not jobs were not just like now. Well, they are very difficult now. But you are lucky if compared to Euler. I mean, jobs. So there was this poster I saw once that said, if you think jobs are hard to find, you should feel lucky compared to Einstein, because he didn't find anything at first. Yeah. Anyhow, so yeah, so he computed this up to zeta of 16, as I said, but you see, this doesn't give us any way to guess what is zeta of 2n. So because it's a recursive, it's a damn recursive process that doesn't lend itself to some pattern like that. It's just it's I don't know how to put it. So let me write here. Maybe there is a method like that. I'm not sure, but that's not what Euler used. Euler did. So yeah, but not in the first attack. In later on. So zeta of 16 is okay. I don't write it again because I wrote it. You see, this was this big fraction, pi to the power 16. So there was something like some rational number Rn pi to the power 16. So with this method, you can guess, you can prove that actually zeta of 2n is going to be pi to the power 2n. That's clear. Some Rn also, no, R16. So Rn pi to the power 2n. I just write R8, sorry, to be consistent with that. But the question is, what is Rn? This was a big question looming for Euler. And so let me write the answer. Euler eventually proved, so this is a big result of Euler. He eventually proved that zeta of 2n is equal to minus 1 to the power n plus 1, I believe. Yeah, 2 pi to the power 2n divided by 2 times 2n factorial b2n, where b2n is the nth Bernoulli number, or 2nth Bernoulli number. So this has the generating function, which is so defined by, so let me put it like this, defined by t over 1 minus e to the minus t equal to sum bm tm over m factorial, m from 0 up to infinity. These are Bernoulli numbers that you can define. So you see, this function is analytic at t equal to 0, because if you put t equal to 0, you get 0 over 0, but you clear the using L'Hopital, this becomes an analytic function. This has a limit, is nice at 0. So it's a power series, you expand it in terms of t to the power m, and this pops out the coefficient. So you can say that, yeah, this is the exponential generating function of Bernoulli numbers. And these are the ones that appear over there. So now, of course, the question is, why, again? Why these numbers appear in the formula for zeta of 2n, and where these coefficients come from. So these are the, but you see, this is a general formula for any even positive even integer. This is so this it's not very difficult, but it needs another idea. The first idea of Euler cannot be applied to get this far. So, I mean, this is not part of what we want to discuss. So, you can read it in many sources now. Yeah. Any questions or comments? Bernoulli numbers, by the way, B1 is minus yeah, okay, so B2n plus 1 is equal to 0 for all n bigger than or equal to 0. Or bigger than or equal to 1, sorry. All odd Bernoulli numbers starting from 3 are 0. You can prove this using this relation. But that's not what we want to do. So, any questions? Or? One of the things that you can conclude, one of the results you can conclude from this is the values of zeta function at negative odd integers. You can compute those. So let me write it down, because this is a nice formula. So this is star. Corollary of a star is that zeta of negative 2n plus 1, negative odd integers. How did I write it? Oh, okay, so I just wrote it as this, yeah, zeta of minus n is equal to -1 to the power n, b n plus 1 over n plus 1. Yeah. So, of course, I mean, this contains the formula that at negative even integers, they are 0 in view of this fact that I wrote here. This contains the old thing that you can also do. But now, to derive this, you have to use functional equation, because functional equation involves s and 1 minus s, right? So relates even and odd in values on two sides of the line, right? So just prove, use star plus functional equation. So yeah, basically now by this, you know, plenty of values of Euler, for example, let me write some values for fun, e.g. zeta of -1 is -1 over 12. That's the famous YouTube fun 1 plus 2 plus 3 plus 4. They want us to accept this as some mysterious identity. Now you know it's coming from this one. So zeta of -5, they never tell you what is zeta of -5, which is -1 over 252. These are just Bernoulli numbers that now you can open the Wikipedia page and you see the Bernoulli numbers. They're all there. Or ChatGPT maybe has Bernoulli numbers, I'm not sure.
They added a Wolfram alpha add-on to it, so probably Wolfram alpha has it, so it probably does have it.
Yeah, I noticed it also processes text.
Oh, really?
Yeah. That's really good. What trouble? It's good. I don't think so. No, I don't know. I think it's depends on your perspective, right? Zeta of -7. Those poor undergrads who suffer through all these exams, they enjoy this. 1 over 240. No, this is positive. Yeah, yeah, this is a good point. Bernoulli numbers oscillate between positive and negative. They are kind of wild. Yeah, but the only regularity is that odd Bernoullis are 0 beyond 1. 1 is not 0. E1 is not. Huh? Or -3 is 120. Yeah, I have it. And they all follow from this formula here. Knowing Bernoulli numbers, of course. I mean, computing Bernoulli numbers has been computed for infinite number of digits. I mean, n's has been computed. Large, very, very large, been computed. Oh, it's unbelievable. Okay, I think we are good for now because we can just, because we're going to take a new turn. So next topic is going to be the explicit formula of Riemann and von Mangold that I mentioned. So we're going to relate now zeros of zeta to prime numbers, distribution of primes and the zeros of zeta when we relate. This is the major theme of Riemann's paper. And in fact, that's why he wrote the paper. I mean, okay, these things so far has been just fun, it's good, but it's not essential. The essential thing is what's going to come next. I mean, okay, it's essential, all of it, but in a sense, the deepest thing is yet to come. What's that? That's Frank Sinatra's song that there is something says fun is going to start or something. Just he talks about his life or something like that. My way, but there is no, but there's another song. It's another song. Yeah, my way is funny. Yeah, everybody sings that. Yeah, most people have had most normal lives, but then they write this inscribe on their tombstone. I did it my way. What my way? It's just a normal person. What do you mean I did it my way? It's so funny. That's okay, sorry. So yeah, let's just stop now before I incriminate myself in front of a world, right? Okay, guys, yeah, I think we are